Um, Good afternoon, everyone. I'm sorry for a little delay. I believe everything is working now. I'm really glad to see so many people. We are changing the place every time, and every time I have some problems to find the place myself. So it's really great that many of you are here. Okay, so what was the last thing we discussed on the previous lecture? You see it's also a different board. I'm not sure how it works. On the previous lecture, we discussed a diagrammatic technique with the green functions for disordered system, and we have found a few basic things. First, we found that there is an average green function, retarded or advanced, which equals epsilon minus psi of p plus or minus I over 2 tau inverse. This is one very simple result. And another, a bit more sophisticated result was that the diffusion propagator can be also found from this method, and it is given by an average of a product of two green functions with, as we discussed, with the possibility to insert some impurities. Yeah, actually it's, how do I do this? And the result is the standard one. It's dq squared minus I omega. And also before this, we also had something which is called self-consistent Born approximation, which is the approximation when we are not intersecting these dashed lines. And this self-consistent Born approximation was the following equation, that the self-energy equals 1 over 2 pi nu tau integral over all momenta d dp 2 pi to power d, and the green function here, which is epsilon minus psi of p minus sigma. We will need this equation later, that's why I remind you how it looks like. This equation is the equation for the self-energy, which takes into account all diagrams without intersections, and this equation gave us this I over 2 tau here. And also, from all these results, Can anybody tell me about this board? Can I
Yes.
Scroll it?
Two fingers, I guess.
With 2 fingers? It's 2 lines.
Maybe you should put select and then
Page number.
Yeah. With select, it works. These are results of the last lecture, and now I would like to show you one more thing that can be done in a similar fashion, which is called conductivity. We have diffusion, propagator, and we also had conductivity. They are related, as you remember, by the Einstein relation. But conductivity we can also calculate using diagrams, and this is also called the Kubo formula. Kubo formula for conductivity. conductivity equals 1 over 2 pi. Very similar thing, two green functions, one retarded, one advanced. But in every vertex, it's called vertex, this point, we insert a current operator, J, and here also J, with index X, and then this thing should be averaged over disorder. I will right now explain what this whole means. Current operator is an operator, is a quantum mechanical operator that corresponds to a measurable quantity, which is the electric current. Current operator is a vector, because current is a vector, J, and it equals just electron charge times Fermi velocity, which is also a vector. Sorry?
Why is it an operator?
Because Fermi velocity depends on momentum.
And it is
So in momentum representation, it's a function, but okay, if you like, velocity depends on momentum, and momentum is an operator.
Fermi velocity.
Fermi velocity, yeah.
So we're like kind of on show.
You can put here just velocity. I mean, we will anyway take it on the Fermi level. So, yeah, that's a good point. I can erase this F here with the rest of the formula. It's just velocity as a function of momentum. So, about green functions you already know. They are these things. These things here. And I can also move it left and right. Interesting. So it's quite similar to the diffusion propagator, just with different objects in the vertices. And also, it is calculated at zero frequency, at zero momentum. So I will just put it right here. And look, this is a vector, and here is the x component of this vector, which means we measure conductivity along the x direction. We apply electric field in the x direction, and we measure the current in the x direction. We can put some other components here, will be conductivity in some different direction. Yeah?
Just to make sure, we're still talking just about the free electron model with disorder.
Yes.
Single part.
Yes. So, this one is much easier than the diffusion propagator we did last time. So it's 1 over 2 pi, an integral. And now I will not write over all momenta integral. I will just do what I do usually, nu times d psi. And here I will have two green functions. Each one produces a denominator, e minus psi plus I over 2 tau. This is a retarded one. And epsilon minus psi minus I over 2 tau is the advanced function. And in the numerator, I should put these two current operators, which will be electron charge squared, and then x component of the velocity, v x squared. This is not so, can I? No. This Vx squared. And disorder average, no, sorry, not disorder, the replacement of momentum integral with the psi integral also implies that we average over the directions on the Fermi surface, of the directions of V. Yeah.
This is replacement always legal, or we can do it because of symbols?
This replacement works well if the integral, if the momentum integral comes from the vicinity of the Fermi surface. So we do it, we do this replacement, then we do the computation. If we see that the integral converges and everything is nice, then it's fine. If it does not converge, it means we should use some better approximation which works not only near the Fermi surface. So this is a very simple integral. And let me do it. So we have nu, we have electron charge squared, we have V Fermi squared divided by 2 pi and divided by d, because we have here only the x component of velocity and we have d components in general. So V squared is if you sum over all d components. If you need only one of them, you divide by d. And then the rest is the integral over d psi. And in the denominator, we have epsilon minus psi squared plus 1 over 4 tau squared. I just multiplied the two things. So this integral is, as far as I can tell, 2 pi tau. Yeah, this is a standard integral, like this arctangents thing. It's from minus to plus infinity, of course. So 2 pi cancels. V Fermi squared times tau divided by d is the diffusion constant. And the result is something that we have already seen before. So this is exactly the Einstein relation that tells us what the conductivity is in terms of the diffusion constant, and we have derived it directly from this diagram, this single diagram, without first deriving what the diffusion constant is, what the diffusion is.
Sorry?
Yes?
Can you explain this diagram, Kubo formula? Usually, Kubo formula is written as anti-commutator of current current. How it
This is something that I didn't want to delve into in these lectures. You're right, there is a very general Kubo formula for any response of anything, and it has an anti-commutator, actually rather a commutator. Commutator, and it also involves some time integration. Two operators taken at two different moments of time. But this is the formula written in the second quantization way. You should replace these operators by the fermionic operators, and then you will have, with two operators, you will have 4 fermions. You apply Wick theorem, you will get 2 green functions, and then basically you will get this thing. But actually for conductivity, there are a few more steps to get to this equation, because I don't have any energy integration here or time integration. This formula works only at 0 temperature. There is a more general one which involves also energy integration, and there is also a distribution function here, the derivative of the distribution function. So at 0 temperature, this derivative is a delta function, so it removes the energy. I just didn't want to go into all these details, but this is how you can compute the conductivity at 0 temperature in a system without any interactions, just single electron. It's only the momentum integral here.
Sorry?
Yeah.
The result tells us that if we put more impurities, conductivity will increase linearly.
Will decrease.
So D is the parameter of diffusion, right?
Is the diffusion constant,
More
yes.
impurities,
More impurities
diffusion.
means less d, lower d. D is proportional to tau, to the mean free time. The more impurities you have, the shorter is the mean free time. So the smaller is d. In a clean system, d is formally infinite.
So experiments confirm this dependence.
You mean sigma on d, or what dependence?
Sigma on impurities.
Yeah, sure. The more impurities, the less sigma.
Yeah, because this is dependence, right?
It was confirmed, I believe, well before quantum mechanics or anything like this. It's from times of Ohm, which is 19th century. Okay, so this is not yet the end for the conductivity, because as you remember, we did the calculation last time for the diffusion propagator, and it was not enough to take into account this diagram with two Green functions. We should also include the ladder inside. So what I did here, I actually wrote two average Green functions. I did not average the product. I take the product of two average functions. So what will happen if I try to insert an impurity here with two current operators, as usual? I will have, let me do it differently. I will take only one current operator and only two Green functions and one impurity line. I compute half of the diagram, not the whole one, only half of it. So, so this would be an integral nu dxi, as usual, divided by 2 pi nu tau, this impurity line, and then I will have the same denominator as there, plus 1 over 4 tau squared. I'm not sure why I'm writing all this, because in the numerator I have only one current operator. One current operator is one velocity. And this thing should be averaged over directions of velocity, so actually this is immediately zero. You see, in this diagram we had two current operators inside a single momentum integral. Here, inside a single momentum integral, we have only one current operator. That's why whenever you draw a vertical line, whenever you split the two current operators, you get immediately zero. So actually this proves that what we did with this diagram is already the complete result and nothing is to be added. So, is this clear? The conductivity? So I will right now.
If you wish, you can create one more page and switch between them.
I can create one infinite page. So I will take advantage of this very fancy board, select some interesting color, say this one. So conclusion from all these previous things. If we include only non-crossing impurity lines, non-crossing impurity lines, I will just write impurities. We always get the result of classical physics, nothing quantum, just simple classical physics. So, just to remind, we started the very first lecture with the diffusion equation, which is purely classical equation, no Planck's constant, no nothing, and we derived the diffusion propagator. Then we did all this quantum stuff with Green functions, with diagrams, and we found that if we do not intersect impurity lines, we reproduce the same diffusion propagator. And this is another classical result, which is the Kubo formula, which is the Einstein relation between sigma and d, and we also reproduced it just by computing the diagrams without crossing impurity lines. And this is a general statement. If impurity lines do not cross, from quantum mechanics, you can reproduce all the classical results. And the opposite statement is also correct. If you want some quantum results which are beyond classical physics, you should include some impurity lines that cross each other. Okay, that's... Yeah.
But actually, in the previous lecture we discussed that if we renormalize the Fermi energy, taking trivial parts of this diagram sum into account. So is it also a classical result or not?
It's not a result at all, because this renormalization is something that that exists only on paper but cannot be measured. So this renormalization is needed to correct some strange things appearing in your strange theory, but nobody can measure how this Fermi energy actually changes. So it's not an observable quantity. Yeah.
Even if, for example, takes metal, clean metal, and then we measure the Fermi energy inside, and then we put some impurities, and try to see how the Fermi energy changes. There is no such experiment. I mean, the question is, what is the clean metal, of course.
Yeah, this is a good question. I mean, I don't know how clean is the clean metal, but what you are saying, you can do it in your imagination, but I don't think you can really do it experimentally.
So is this statement true only at 0 temperature?
This one?
Yeah.
Actually, no. Actually, it's correct also at finite temperatures. But it concerns only disordered systems. So if it's about crossing of impurity lines. So if you want to study disorder effects classically, you can, if you study disorder effects and include only the diagrams where the lines do not cross, you will reproduce classical results also at finite temperatures. But if you include something, not just impurities, but some other things like Coulomb interaction or other things, then it's more complicated. So this concerns only impurities. But this is correct at any temperature. If you have only impurities, this is correct.
Even though the spectral function, like classically, is a delta function, while in this picture, the quantum picture, it is a Lorentzian.
Spectral function? What do you call a spectral function? Or you mean this thing here?
It is broadening, and if the temperature is finite, this would...
This is a green function. It's not actually a spectral function, and this is not really broadening. It just tells you that the average green function decays with time, but only because it is averaged. There is something like a true green function, which will not decay. Now, if you have finite temperature, you still have this expression for the green function, but your electrons, you have many electrons, and you have some distribution function, which energies are occupied, which are empty. You have this Fermi distribution, and you should also take into account that this energy variable here should be, you should integrate over this energy with the distribution function. Then you will see what happens at finite temperature. But this broadening, this is just a single electron green function for an single electron green function for the electron which does not interact with anything, only with impurities. So it's like there is only a single electron in the whole world. It has a certain energy and it scatters on the impurities and tries to diffuse through the system. For a single electron, you cannot even define what temperature is. But once again, if you have many electrons, then temperature is just a different way of saying what energies are occupied and what energies are empty. So if you know how a single electron behaves, you can then take into account many electrons and find the result for any temperature, even for some non-equilibrium states without any well-defined temperature. It still works. Okay, are there any further questions concerning this? Yeah.
Just thinking about the Kubo formula that's written there, maybe you can tell a little bit more about the equation behind it, because like this function in any way it's like electron propagates to one side, then it somehow propagates back, and there is this averaging which also has subsets which I don't understand. It's like maybe scattered on many impurities for one electron.
Okay, once again, I would not like to derive this Kubo formula from the very beginning. It will require a separate lecture or two. I will say just two things. Kubo formula is also correct without averaging. So this averaging is needed, but I mean, for a given realization of disorder, you can still measure the conductivity, and it will be given by this product of exact green functions. So before averaging, this identity is already correct. I did average here just because I want some average conductivity. What I found is the average conductivity, not any given one. So Kubo formula actually works without averaging. And second thing about intuition, you have these two current operators here. Actually, Kubo formula can be written for any linear response. You have your system, which is in some ground state, for example, and you apply a small perturbation, some external force, which drives it out of this equilibrium or ground state, and then you can measure some quantity which is the response to this applied force. And for conductivity is one of possible responses. When you apply electric field, this electric field induces the current, you measure this current, it's a linear response, small field, small current. So what we have here, this one, the current operator here on the left is the one that we measure. And this other one is the perturbation that we applied, because perturbation is current, the electric field is itself coupled to electric current. Well, actually, it's vector potential, which is coupled to electric current. So we have a small perturbation in the form of the vector potential, and then we insert it inside the green function, and then we measure the other current. So you get this diagram like that. This is the point where electric field was applied. If you like, electric field was applied. It induced some excitation. Some electron was excited. Then this electron propagated to a different point, and there you measured the current. And then you integrate over all momentum, which means you integrate over both points. Actually, you have a Kubo formula where you can have any two operators here. Any operator can be a response to any perturbation. This formula is derived just from a very general perturbation theory, like in general quantum mechanics. Okay, let's move on. We can always scroll back if you want to see something there. So, as I just said, classical physics is the result, can be derived from quantum physics, from these diagrams, if we take into account non-crossing diagrams. So today will be the first time we are discussing some really quantum effects which have no analog in the classical limit, and it means we will include some diagrams with crossed lines, but it will be later. And right now the topic, I can use any colors. The problem is I don't know which colors are better. Let's say red. So the new topic is, it was supposed to be red. It's red on the other side. Scaling theory of what? Of localization. I will explain what is localization and what is scaling. Localization. So, I will right now show you some example of a quantum effect, but it will not be, it will come almost without any calculations. It will be just some qualitative discussion. Scaling theory is a qualitative theory. So imagine you have a piece of metal which has a form of a cube. Oh my God, what's happening here? Give me back my usual pen. You have a cube like this. It's a piece of metal. This cube has a size. This size is called L. And you measure the resistance of this object, just electrical resistance. You attach two contacts here, you pass the current, you measure the voltage, divide one by the other, you know what the resistance is. But actually, in theory, it's easier to talk about a different quantity, which is called conductance. Conductance, G of L. It's just by definition the inverse resistance. You take the resistance, you invert it. What you get is the conductance. So there is a conductance of this cube. Conductance means, so resistance is voltage divided by current. Conductance is current divided by voltage. And it depends on the size. If you make the cube larger, it will change, the resistance changes, the G changes, and this is what is called scaling. How the quantity depends on the size. It scales with the size. So, question, how does conductance depend on this size? This is some middle school physics problem. I don't know if children still study physics in middle school. So, you know how if you have a resistor and you attach resistors in series, the resistance adds up. If you attach them in parallel, actually the inverse resistance adds up, so conductance adds up. So if you have a cube of the size L and you double the size, you take 8 such cubes and you stack them in a bigger cube, you can say that the conductance as a function of L, of its size, is proportional to the size itself to power d minus 2. D is 3, is the dimension of the space. Why is d minus 2? Well, the dimension of the cross-section, if current flows in this way, the cross-section has a dimension d minus 1. So conductance scales as L to power d minus 1, and it scales inversely proportional to the length. So you divide by one other L, so you have d minus 2. This is just a simple consequence of how resistors are added up. So this thing is actually called any material that shows this type of scaling, where G scales like this with L. Any material of this type is called a metal. Well, in a very general sense, any metallic thing which conducts current will do this stuff. And actually, there is a second type of material which is called an insulator. For example, what is insulator? Insulator is something where you don't have mobile electrons inside. Just the air here in the room is an insulator. There are no free electrons. So, what would be a conductance of a cube of an insulator, and how does it depend on the size? Now, this is a quantum thing. That's a classical, this is like an Ohm's law. Now, the conductance of an insulator is a quantum notion because there is nothing to conduct. So, if you have a piece of, I don't know what, plastic, you attach two contacts and you ask what will be the current if I apply voltage. Classically, there is no current. But in quantum sense, electrons still can go from left to right by what is known as tunneling. Electrons can tunnel through a barrier which doesn't host any classically allowed states, and tunneling from here to here is exponential, the probability of tunneling is exponentially small. So actually the conductance will be some exponential function which decays with the length exponentially, and just to make it dimensionless we should divide by some other length which I will also call psi. This is called localization length. This is localization length. So actually it's a bit different than in usual insulators. Imagine you do have electrons there inside this material, but they're localized. They're pinned to some positions and they cannot move. But these points where they're localized, they have a certain size. So they're like sitting in a potential well of a certain size and can move only back and forth like this. Then you can estimate the tunneling probability as the exponent with length compared to the size of this localization. So this limit here is called an insulator. A metal and an insulator are two types of materials that have different scaling of conductance as a function of the size. So far nothing new is said. I mean, it's just some hand waving, right? Now I will write here a statement which is very non-trivial and which is not obvious but which is correct. And then we will use the next 5 lectures to prove it. Maybe not 5, I don't know. Statement. Very important statement. What's this? Yeah. Derivative of the logarithm of g, this g, with respect to the logarithm of L is some function, unknown function, of g. End of the statement. This is a very important thing. This is called scaling hypothesis. So it's not proven, it's just a hypothesis. Or in other words, this derivative of logarithm of g with respect to logarithm of L depends on g itself, but what's the matter? It does not, the right hand side does not contain L. This is the main part here. Yeah.
Sorry, but actually if g is a function of L or L is a function of g, we always can say that any derivative also is a function of g.
Look, you have many different materials. You have many different metals. You have iron and you have aluminum. Are you sure they both will have the same thing here?
Or you mean that you have, for example, 2 different cases and this this hypothesis unify both of them? And
Well,
many others?
let me put it differently. Imagine you have a single material, but are you sure that once you know the so actually you're right. I can invert this equation and say that if L is the function of G, then I take a derivative and it's another function of G. Are you sure that knowing the conductance you can uniquely define what L, solve the problem and find what L is? Is L dependent only on conductance and on nothing else? Yeah, that's a very weird way to formulate the question, I understand. Usually G depends on L and not vice versa. But what you are saying is that G is a function of L such that it can be inverted and you can find the function L is a function of G universally. Such that L depends on G and on nothing else. Just imagine here G depends on L and also on psi, right? Or if you have some more complicated thing, you can have other parameters entering here, so you cannot just invert the function uniquely.
So is the function the same method?
This is a good question. Beta function is universal to a very great extent, but it's not just the same function always. There are a few options what it can be.
For example, here we have metal and silicon.
Oh, that's a single function. Yeah. Here it's just a single function. Yeah. Once again, this statement is a hypothesis. I didn't prove it. I just stated it. And it was first stated in a paper written in the year 1979. And it was really a revolutionary thing because nobody believed it. And it took a few years when people actually found how to prove it. So it was first stated using some hand-waving arguments, which I will not reproduce here. I will just prove this formula within the next 5 lectures. But I will just illustrate how it works right now.
This is the same G of L. The G of 2L is a function of G of L.
In a sense, if you know G of L, you can find what G of 2L is without knowing any microscopic details. If you know what G of L is, you can then integrate this differential equation and find G at any other value of L.
So you could formulate the hypothesis as G of 2L is...
Depends on G of L and on nothing else. Yeah, that's true. Okay, so just illustration. We have for metals and insulators, we have this quite simple forms how G depends on L. In metal, it's one dependence, in insulator, it's a slightly different one. So let's calculate what this derivative is. D log G by D log L equals, we have two cases, metal and insulator. So for a metal, I take a logarithm, I have D minus 2 times log L, so this derivative is just D minus 2, it's just a number. This is for metal. And for the insulator, if I have an exponential here, I take the logarithm, it's minus L over xi. Then I take the derivative with respect to log L, which makes it just L. And then this L is the logarithm of G itself. So you can check it's the logarithm of G. Logarithm of G is minus L over xi. And this derivative is the same thing. Wait for it. So this is an insulator. Yeah, these two things are very different, that's correct. So, what should I do? Yeah, let's do it here. Let's draw a plot of this function. This vertical axis will be the derivative, the left-hand side, which is d log g divided by d log L. And the horizontal axis will be the right-hand side, which depends on g. But I will write here log g. Well, g log g. It's just a function of g. So, if we are in a metal, this thing is a constant. It does not depend on g. So, this should be a straight line. Say d equals 3, d minus 2 is 1, so this is a line at the height 1. And usually, we know usually that metals are good conductors. They conduct well, they have low resistance. So for metals, it's quite natural that this constant is at some large values of G. Metals usually have large values of G. And insulators usually have low values of G. They're very poorly conducting. So somewhere here, at low values of G, this function should be a linear function like this. Yeah, derivative equals log g. I have derivative here, log g here, so it's just a linear function. Somewhere in this part. So the scaling hypothesis actually tells us that there is some single universal curve that connects these two limits. So there is a single function how this derivative depends on g, which applies in one limit to metals and in the opposite limit to insulators. And also describes how they are connected.
It depends on the number of dimensions.
Yes, in 3 dimensions it should look something like this. In 2 dimensions it's a different function. So for metals d equals 2, d minus 2 is 0. So it should be a linear function that somehow approaches 0. This is for d equals 2. And for d equals 1, it's some linear function that goes to a constant which is minus 1. So, you see there are different functions in different dimensions, but in each dimension it's the same function for metal and insulator. It's just, and I will write it here. Metals is something that has large g, and insulator is something that has small g. So once again, this is a hypothesis which is correct, at least in the limit of classical metal when Ohm's law applies, when this derivative is d minus 2, we just know what this function is. And this value, d minus 2, knows nothing about the material. It's the same for metal, for iron, and for aluminum. It's the same for anything. It's just the same number. It knows only that your object is 3-dimensional.
Can you define the superconductor on this diagram?
No. You see, we have metal, we have insulator, but we don't have a superconductor in this list, so it's not in the diagram. Yeah.
Is it on the slides negative for d equal to and for d equal to? Like for d equal 1, it's always a
Well, it's because d minus 2 is negative for d equals 1. Oh, well, it just means that if you have a one-dimensional sample and you increase the length, your conductance decreases. That's why it's negative. The derivative is negative. For 2 dimensions, it stays the same. If you have a square, a 2-dimensional square, and you increase both sides, length and width, it's 0, 0, 0. It will stay fixed.
Kind of again. how I should connect scaling hypothesis with this plot.
So there is a hypothesis which tells us that this derivative it should be a function of g. This plot doesn't prove anything. We just attempt to plot this function, and we know that in two limits, which are metals, good classical metals, and good classical insulators, well, quantum insulators, no. In the two limits, this function looks like either a straight line here or a straight line here. Then, if this hypothesis is correct, which we have not yet proven, this should be two ends of a single function. So we just draw like this. I mean,
The point is that it's independent on which material we consider. Or,
yes. It's not exactly independent. For example, it depends on the dimension, right? So it's not the same for any value of d. There are some other things which it can also depend on. I will show it later, more accurate thing. But for usual metals, without any sophistication, for usual electrical current, it should be just a single function. If, once again, if this hypothesis is correct.
if this hypothesis is correct, it means it should be like smooth function.
Yeah. Well, and actually, if this hypothesis is correct, if this plot is correct, if this function looks like this, it really exists, really universal, it means universal, yeah, it's the function of g, which does not know anything about your material. It's all, the other way to say this is say that this is a universal function, which universally applies to many different materials. So if this whole thing is correct, we can now give a better definition, what we call a metal and what we call an insulator. Definition. Whenever this derivative, or whenever this beta function, beta of g, is positive, if beta of g is larger than 0, we will call this a metal. Whenever beta of g is negative, we will call this thing an insulator. This is a definition. Definition of these two words now.
We don't have one-dimensional metals.
I don't have. Look, you take some material, I don't know which one you like, of a piece of a given size L, and you start increasing this size. You make it bigger, 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 and bigger, and you know that this derivative tells you how the conductance changes. So if this derivative is positive, somewhere in the upper part, you make it bigger, 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 conductance grows. This is a metal. Yeah, metal can have very good conductance, even if you take a very big piece of it. If you increase the size and conductance decays, then in the limit of infinite size, you will have 0 conductance. This is called an insulator. Now, if we look at this plot, we see that in 3 dimensions, we have a beta function that goes from positive to negative at some point.
Now, but why you assume that it should be like connected inside? Like, why these two beings can have, I don't know, some step or something like that?
I just connected them in the, let's say, in the simplest way I can imagine. Of course, this might be a very strange function, or this hypothesis might be wrong and there is no single function. But once it is correct, I just assume the simplest, the smoothest way to connect. Yeah. Not me, actually. Some people before me did this.
What's the question about d equal to 1?
I will answer this question in 2 minutes. So, in d equals 3, if this plot is correct, it's like, you know, every sentence is prepended by this plot. If this statement is correct, then in 3 dimensions, function, this beta function, can change from positive to negative depending on the value of g, which somehow disappeared. There was g here. Yep. If we have some good material, like, say, we take a piece of iron, we measure its conductance, it is somewhere here. We say, aha, beta function is positive, it's a metal. Let's increase its size, and g will increase. It will, if you like, go this way. I don't know how this whole thing works, sorry. It will grow. But if you take a piece of wood, which is usually an insulator, you measure conductance of the same size, same piece, and you see some small conductance, you look at this plot and say, aha, we're somewhere here. If we increase the size, it will go to 0, so this is an insulator. So in 3 dimensions, there are materials that are metals, and there are materials that are insulators. And even in a single material, this is the answer to your question, Diva. If you take a good metal and you add impurities to it, tau gets smaller, resistance grows, and you can add so many impurities to a metal that you will cross this point. At the same size, your conductance goes down, down, down. Then you say, my sample, my material, this metal, undergoes a metal insulator transition. It was a metal, and it becomes an insulator when the number of impurities exceeds some critical value. This is a critical point. This is called a metal insulator transition critical point. This happens in 3-dimensional world. Wait, please. In 2 dimensions, as was mentioned already, looking at this plot, we see the function is always negative. So even if we take a good metal with a good conductance somewhere here, with few impurities, and then we increase its size, since this function is small but negative, it will eventually go here, and when the size is 1 light year by 1 light year, we will see that it became an insulator. So, and in 1 dimensions, it's even better. I mean, they are all insulators, no matter what you do. Sorry?
When you increase size, the beta is fixed, no?
No. Beta is the derivative with size. So when you increase the size, your g changes. If this derivative is positive, it means g grows. So you go to the right on the g-axis. If the derivative is negative, you will go to the left on the g-axis with increase in size.
Y-axis is better.
Why? What is better?
Beta is the y-axis.
No, it's just what I plot. You see, this was my scaling hypothesis that this derivative is beta. So this is what I plot, beta of g.
So, I have a situation when beta equal to 0.
This is called a critical point. This here beta is 0. It's the transition point between metal and insulator.
It's only a 3-dimensional case.
No. In 3-dimensional case, beta also crosses 0 at somewhere. This point is 0.
And I actually, okay, I ask again. Beta equals 0 exists only in 2-dimensional case.
No, it also exists in 3-dimensional case.
I said 2-dimensional.
In 3-dimensional case, it exists here.
Exactly what I said.
Sorry.
Reverse set of 3-dimensional, you heard them too.
Maybe, yeah. Beta, this point exists in 3 dimensions, and according to this plot here, it does not exist in 1 or 2. And this is an interesting statement, which should be also with some strange color. Give me strange color. That doesn't work anyway. It works like this. No metal in 2 dimensions or one dimension. Metals exist only in 3 dimensions. This is a very provocative statement. Actually, it's not correct. It's almost correct, but not exactly. We will see later a better statement. So this is an outcome of this scaling theory as long as this scaling hypothesis is correct.
As long as we define a metal by this.
Yes, according to this definition. That's true. Yeah.
How do we know that in 2D we do not cross the... How do we know that in 2D there is no metal?
We just look at this plot and we see that beta is negative.
Arbitrary plot, right?
Yeah.
We could just cross it and then it would be a bit negative. We just said, okay, we know that at infinity we are at 0, but we don't know that.
You know, even in 1 dimension I can create a metal if I connect this line to this line by something that shoots up above 0 and then goes back. Why not? I don't know. This is just the simplest way to connect to limits. There are less simple ways that can lead to existence of metals even in 1 dimension. And this whole thing is yet to be discussed, studied, and I will give you a lot of examples what can happen. So right now it's just the simplest, the easiest way how we do this. Maybe we're right, maybe we're wrong. We will see. But if we are right, if this simplest way of connecting two limits is correct, and if this scaling hypothesis is true, then this is our conclusion, which was a big surprise 50 years ago, a bit less than 50 years ago, when this was first discovered, let's say it like this. Yep. What about them?
There's like hopping between sides, and we see it's like metal, and you have cosine dispersion.
It's not disordered.
So now there is no metal because of disorder.
Now you add impurities, and you grow the size, and you see that your conductance goes to 0.
So the adding dimensions works only for the case of disorder.
If there is no disorder, formally conductance of your system is infinite. Conductivity is infinite. So I'm not sure that you are anywhere on this plot if you don't have disorder. You are somewhere infinitely far there, and yes, with increasing size your conductance will decay and eventually you will get here, but it will happen after an infinite increasing of the size. So you need some disorder to get to a finite point on this plot. Okay, so as I said, this statement was very controversial. Nobody believed it, just like you now do not believe it, like I did not believe it when I was in your place. And to be convinced that it is correct, and actually it is correct, it is almost correct in this way with some little modifications that we will see. We will do some calculation. So the most interesting part of this whole curve is here, is d equals to 2 dimensions in the metallic limit. Well, sorry, there are no metals in 2 dimensions. In the limit of large G. If classical physics is correct, then beta function is just this d minus 2. Yeah? There are just metals, we have Ohm's law, there is nothing else, there are no insulators, there is no tunneling. If classical physics is correct, and dimension equals 2, this function beta should be exactly 0. However, if we have some quantum mechanics that provides corrections to the classical results, this beta function can deviate from 0. And here, when G is large, when we're in a system with large conductance, when disorder effects are weak, we can do our usual perturbation theory in disorder as we did, and we can find this is a small correction. We can use perturbation theory to find a deviation of this curve from 0 in this limit. let me finish, please. And this will be the next topic, which should be written in some other random color. It's called quantum correction to conductivity. So when I say quantum correction, it means there is some classical conductivity, which we discussed in detail, which obeys the Einstein relation, which is related to the diffusion constant, all these things. And this is a classical result. Now, we do something beyond classical physics, and we find some small correction, because classical physics usually works well, all quantum corrections are usually small. So we will compute quantum correction, what quantum mechanics, how it changes this classical result, and it will tell us what this beta function does actually in a certain limit. Yeah?
Just for the sake of, like understanding the scales. So let's imagine that we have some, really nice piece of metal, which is very, very classical metal. It behaves just like scaling hypothesis says. Okay?
Even bad metal behaves like
Yeah,
it
even,
says.
okay. Nice image.
Yeah.
So, what size of a metal, physical size, literally like millimeters, I should think of as a limit L goes to infinity?
In which dimension?
In 2, for example?
Exponentially large.
Large.
You see, this derivative is the derivative of with log L. So to do something here, you need log L to be large, which means exponentially big.
Okay.
In one dimension, it's just
But in,
power law big.
is it possible to think of something like really physical sizes or not?
Well, look, if you ask in millimeters, or I don't know why not.
I'm asking rather about what size of crystal I should think of.
It depends very much on a particular material, because this derivative is universal, but the length scales are not universal.
Okay,
So there are materials where you can see it in a very small size, and there are materials which will require you to go to the moon and back to see that it's an insulator. So this statement that no metals in 2D means that even a very, 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 very clean and good material, if you make it of the size of our galaxy, will have a zero conductance. Maybe beyond our galaxy.
What do we actually want for this theory? I mean, as far as everything depends a lot on the particular properties of the metal, what do we want in general?
This beta function does not depend on properties of your material. It depends only on the dimension. There are just 3 functions for all materials in the world. This is a very universal thing.
So we're just chasing the universality.
So for different materials, you take a cube, small cube, 1 centimeter of different materials. You have 10 of them, and they all have different conductance. Which means you are on this curve for d equals 3, but you start at different points. That's all, but it's the same curve for all of them.
But I mean, like the general point of all this calculation is to find some universal behavior that's
Yes. Okay, well, so quantum correction to conductivity. Let's do something quantum in the end. First of all, is it? No. First of all, we will do it, let me think. Yeah, never mind. We will do it for a general case. First, so conductivity, sigma, is given by a Kubo formula, which we just discussed in the very beginning. 1 over 2 pi and 2 green functions with 2 current operators. and the functions are retarded and advanced. And this diagram gives us the classical result. Just these two green functions, we integrate them, we get usual diffusion constant with all the prefactors. So now we should include something in this diagram, something which was not included before, namely some crossing impurity lines. Some impurity lines that cross each other, which means it will be a quantum effect not encountered in the classical limit. And we will actually insert many such lines. It's called a fan shape diagram. For example, here I have 4 dashed lines. They all cross like this. It looks like a fan. Is it a fan? I mean, this thing that you. No, fan is rotating one. And what is this? There. Yeah, it should look like. So it's fan. It's also fan in English, I believe. So it's a fan shape diagram. And of course, it's not just a single diagram. It's a whole series. You can have 1 line, 2 lines, 3 lines, 4 lines, 5 lines, and up to infinity. It turns out that all these diagrams are small. Each diagram provides a small correction to the classical result. But all of them, each of these diagrams are of the same order. So we have to add up this whole series to collect some meaningful correction. And, sorry?
Why are the same order? But like each crossing is
Depends on how you count the number. So this is 1 crossing. I'm sorry.
Will you explain later why we'll take exactly this diagram and not any other with the crossing lines? For example, we just include correction to single green function with the crossing lines, and
You can add also crossing to a single green function, but it will not provide any meaningful correction. You will see.
okay.
This will be in 10 lectures, not even in 5 lectures, but hopefully you will see. So, oh, it's still red. Sorry. Yeah, so I will just draw the same diagram once again in a different fashion. This is my left point, Jx. This is my right point, Jx here. Then I have this retarded function which connects them. And the advanced function, which is here below, I will draw, it goes from right to left. I will draw it like this. This is my advanced line. Who cares? I mean, green function, it's only, if you like, only the topology matters, which point is connected to which, and how I draw the line doesn't matter. But all these dashed lines here, if I do it like this, will become just like a ladder. And this is the answer why it's only 1 crossing, because it's this crossing of the green function with itself. See, I just took this lower part and I flipped it the other direction, so this whole fan became a ladder. I just have to connect this part to that current operator and this end to that current operator.
This line below also satisfying. Does it sense?
Well, out of the plane of the board, yes. It jumps over it. Yeah, there's nothing, this crossing point is not really any vertex. You can draw it in 3 dimensions, yeah, it will go around. Okay, so how do we calculate such a diagram? We break it into pieces, and the first piece will be just this ladder alone, without all the current operators and all the other things. And this ladder alone has a name, and this name is a couperon. Couperon, sorry, again, I don't know how to place. The couperon is a ladder object with two green functions, one retarded, the other one advanced, goes in the opposite, sorry. The other one advanced, going in the same direction with the ladder of impurities. And this object has we will write letter C, which depends on Q and omega. This will be a coupon. And just as a reminder, earlier we had a different object which was called a diffuson, which looks very similar. Diffuson is a ladder with two green functions, one retarded, one advanced, with these steps here. And this is diffuson of Q and omega. How many of you see the difference? Yeah, just this arrow points in opposite directions. Retarded function points to the right, advanced is either the same direction for Couperon or the opposite direction for diffuson. They are very similar. They are very, very similar. And just to remind you, although we never did it, the diffuson equals, well, we did it and it was dq squared minus I omega. But if you do this calculation for this particular ladder, it will be slightly different. It will have also 2 pi nu tau squared as a prefactor. Well, just because I start the ladder with an impurity line and I end it with an impurity line. And the diffuson that we had before started with an and ended with the density vertex. That is the same ladder inside. I mean, it is the same diffusion pole. It's just a different constant. One impurity line is 1 over 2 pi nu tau. And all the rest, tau times this, is dimensionless. It's to commemorate Nigel Cooper. Yeah. It's called a Couperon because it looks very similar to how Cooper pairs look in the superconductor. It looks similar. Here I don't have any superconductivity in this whole thing, but in a superconductor you have a very similar object which is called a Cooper pair, which is a pair of two electrons that interact with Cooper interaction. It looks like a similar ladder, that's why it's called Cooper. Yes, there is. I will give it a bit later. So, a question to the audience. We studied this diffuson in a large detail, and we know that it behaves like this. Who can tell me what will be the Couperon, the expression for Couperon? The only difference is we flipped the arrow. It was an arrow this direction, it became that direction. So the Couperon is the following. The result for Couperon is the following thing. It's 2 pi nu tau squared dq squared minus I omega. Who can see a difference? There is no difference, right? It's exactly the same. Because green function does not depend. If you flip the arrow, it's like you go from p to minus p, if you flip the value of momentum. So if psi of p is a symmetric function, it doesn't matter. it's the same thing. Because there are two different directions of the arrow. So they're different objects. They just happen to be equal in this case, but they're different objects. Okay, so let's now, sorry, this is not sigma. Sigma is the total conductivity, and this thing here is delta sigma. It's what is called a correction. It's a quantum correction to conductivity. Correction to conductivity due to quantum interference. And we will calculate it. Wow. We will calculate it right now. Delta sigma delta sigma equals, I will draw the same diagram once again, just because I like drawing all this stuff. 1 over 2 pi. I will draw it now in the third way. We have an initial point with jx and two lines going out from here. We have our final point jx with also two lines going here, and then we have a huge loop like this, which contains a ladder inside. Now the arrows, this is a retarded function which goes from here and ends up here. And this is an advanced function that ends up here and emerges from here, and they both go in parallel along this ladder, retarded and advanced. It's still the same diagram, now twisted in a yet different way. It's still a diagram with a single crossing, now it's here. This crossing is here. This is a more intuitive way to think about it, because if you do the diagrams in real space, if your green functions are really electrons that go from this point to that point, it looks more like this than like this fan shape originally. Each green function, as we discussed, decays with time. After tau, it disappears. After time of order tau, it disappears. It also.
I don't know what's meant or not. I guess you should change R to R.
Sorry?
I guess you have a little mistake. You should change retarded and advanced.
You mean this too?
Yeah.
Yeah. I probably thought before the crossing. Yeah, this one, you're right. This one is retarded, this one is advanced. So in real space, each green function also decays. It decays not only in time, it also decays in real space on the scale of mean free path. So each step of this ladder, which contains two green functions, cannot extend in real space further than of the order of mean free path. And you need to stick all these steps together such that this ladder can propagate to some really long distance. Because each step is short, each step is not much longer than mean free path. And these four green functions here, they are also short in real space. They cannot extend much longer than mean free path. Which means, and each impurity is just a single point. Which means that these 4 points, 1, 2, 3, 4, are actually quite close in real space to each other, but this ladder can go quite far away and then come back.
So it's the total quantum correction.
This is, yeah, with, if it has many terms, it can, the more terms it has, the further it can go.
So it's like one term, it's not the full correction.
Sorry, which one term?
I mean, so you said like classical expression and quantum corrections of
Yeah.
And is it a full quantum correction, or it's one term on one, a lot of other quantum corrections?
It's one term, but it's the main term. There are quantum corrections to quantum corrections, and quantum to quantum to quantum. They get smaller and smaller and smaller. So this is small compared to classical, but this is larger than all other quantum corrections.
How many impurities should we include in this diagram?
From 1 up to infinity. You should sum up the whole ladder. 1 plus 2 plus 3 plus 4 plus 5.
You said something about the distance between these pair of photos. What you mean?
It's just a way to imagine how these diagrams occur in real space.
So you're just saying that each impurity is just a point, and distance between impurities it's point.
The green function, the average green function, we didn't do it. You can write an average green function in real space representation, and it will tell you that it decays as the x1 minus x2 divided by 2L with the mean free path, which means that the initial and final point cannot be very far away because the function will be very small. We had this with time. We have the green function decays with time as minus t over 2 tau, so it does the same in real space with length. That's why each step here from this point to this point cannot be very long, because otherwise it will be small. And the same is true here. This is a single point, and this point is not very far from it. And this point is not very far from that point. And this point is not very far from that point. So all these 4 points, 1, 2, 3, 4, are quite close in real space.
Quite close,
Within the distance of the order of the mean free path.
but it's not obvious.
Sorry?
It's not obvious. I mean, it's,
To me was not obvious. I'm sorry if it was obvious for you. So look, when I draw a diagram like this, is it obvious for you that from this point to that point is only about a mean free path?
no, I just thought it's goes from the definition of the
Sorry, what goes from the definition of
distance between these points should be order of magnitude.
from this point? From this point, what is the distance from this point to this point? Can you tell me? From the definition of the mean free
I
path.
thought you said that distance between impurities. Or
Distance between impurities is of the order of the mean free path. That's true.
Yes, so
Now, what about these 2 points?
I was just trying to choose this point.
Just I like this pair of points.
Yeah, everything distance between these points.
Wait, sorry. No. Wait, look, I guess I understand what the confusion is. If you have many impurities and you take one impurity, then the nearest impurity probably will be a mean free path away. But nobody told you that this electron goes to the nearest impurity. It can go to some very other impurity. I mean, we don't pick them here. It goes to where it wants to go. It just turns out that if it goes from this impurity to some faraway impurity, it will not make its way because there are many other impurities in between it, and it will decay before it reaches there.
So your point is
Let's discuss this after the lecture, please. We are getting behind the time very much, and I believe this is not the most important part of this calculation.
Points, so I guess it's
I
important.
promise to explain you every detail after the lecture,
Okay.
if you don't mind.
Okay, it's you, but okay.
Or does anybody else have the same question?
I don't understand the question about the
It's a diagram, which means we should integrate over all distances, over positions of every point should be integrated out. But this integral includes an exponential factor inside, which means that the main contribution to this integral comes from the configurations when the distance between these 2 points is not very long. That's all. And actually this is not important, it's just another way to draw the same diagram. Who cares? We can just compute it and see the result. Who cares how I draw it? Yeah.
So infinity band and back to the hypothesis.
Yes.
So the hypothesis says that infinity band is not a relevant scale. Or
Yeah.
it only holds for the
Actually, it holds only for samples larger than the mean-free path. So for samples where you have many impurities. So, in a sense, you have some scaling at shortest distance, but it's not universal. It becomes universal once you exceed the mean-free path. Well, so what did I say? Yeah. A diagram. This diagram contains a couperon, this ladder here, and it also contains an object which with these 4 green functions. So the diagram, this thing equals an d-dimensional integral over q to pi power d of the product of 2 objects. One object is called hxx of q, and the other one is called the couperon of q and omega, which is equal to 0. And couperon is this ladder here. This one is that, and h xx is the following thing. Is 1 over 2 pi, and these 4 green functions with 2 current operators that are left here, jx, jx, and these 2 retarded functions and 2 advanced functions here. And actually, sorry, it's just a number. It does not depend on q. It's just a number. And this number is an integral, as usual. So 1 over 2 pi nu d psi, 4 green functions, 1, 2, 3, 4. Epsilon minus psi plus I over 2 tau squared. We have 2 retarded functions. Epsilon minus psi minus I over 2 tau squared. We have 2 advanced functions. And we have 2 current operators here. So it is E squared V squared divided by D. It's the same as was in usual conductance. We have V squared. We have Vx averaged over the Fermi surface. And there is one mistake in this formula. Who can spot a mistake? It's very tricky. It's minus. It's minus because it depends on how these arrows are ordered here. So I have 2 arrows going up through this current operator, and I have the other 2 arrows going up through the other current operator. But the momentum, I integrate over momentum. Momentum goes inside this loop in one direction. So it goes along these arrows here and opposite to these arrows here, which means these 2 green functions should be taken at minus p, but it's the same, the green function doesn't change. But also this current operator should be taken at minus p, which means the overall minus.
Isn't the same logic?
Yeah, there we don't have any current operators, only the green functions, that's why it didn't change. But here it will change because, so flipping of arrows does not change. What changes is this current operator, which is inserted in the wrong direction. Okay, so this is a simple integral. It's very convergent. It can be calculated easily. And it's just a number which equals minus 2 e squared nu d tau squared. So you see we have this v squared over d, so we can form a diffusion constant, and then we have this extra tau squared. And correction to the conductivity delta sigma is this number times the integral of this Couperon. This number is minus 2e squared nu d tau squared divided. Couperon, as the same as diffusion, has this denominator from here, 2 pi nu tau squared integral. Let's do it in 2 dimensions. 2 dimensions. Then this q integral will be 2-dimensional, which is q dq divided by 2 pi, and the Couperon is 1 over dq squared, and omega is 0. So that's the correction. It's logarithmic. We have 2 q's in the numerator, 2 q's in the denominator. It's a logarithm. So we should establish some limits. What are the maximum and minimum possible values for this q for such an integral? And the largest possible q is the upper limit is the inverse mean-free path. Because this whole theory with average green functions and with Couperons and diffusons, it only works. Remember, we had this last lecture that QL is much smaller than 1. The diffusion is established at distances longer than the mean-free path, which means Q is smaller than the inverse mean-free path, which means that Q should not go above the inverse mean-free path. And the lower limit is trickier because the lower limit tells you what is the largest possible size in real space. And there is nothing that can limit this Couperon. As I said, it can go anywhere it likes and come back, unless you have a sample of a finite size. And this is the size of the sample, also inverse. It's the minimum allowed value of Q, because you cannot fit a smaller Q, a larger wavelength, in a sample which is only of the size L. So the answer is minus. Everything cancels. And I believe it should be e squared over 2 pi squared logarithm of L divided by L. Can somebody approve? Yes. 2 pi squared, all the rest of it. Actually, I can restore, I always forget it, but there is also a Planck's constant here. Because this is a quantum correction. Now it's a quantum thing, it should contain the Planck's constant. Yes?
Whenever we introduce the upper cutoff on the mean-free path scale, right, we assume that the other part of the integral,
Which is above.
mean-free path to infinity, gives much lesser.
Yes.
Why?
Oh.
As far as we know, ideal.
For this exact problem, I can actually do this calculation. I can find this part explicitly. But the simple reason is it will decay faster than 1 over q squared. When you exceed L minus 1, it starts decaying faster. So it decays as 1 over q squared, the Couperon. This is a Couperon. If you go to very large values of q, you get into ballistic regime. So you have only like 1 or 2 scatterings, and you can compute this ladder more accurately for such large momenta, and you will see that it just goes like 1 over q squared and then drops faster.
Why did we decided to jump to 2D?
Well, because in 2D it's the most interesting case. We can do it the same as in 1 and 3D as well. I mean, in 3D it would be quite a dull correction because it will not depend on the size of the sample. You will have q squared, so it will go to the upper limit. It will be just some number. Well, it will like inverse L here, inverse mean free path. And in 1D it will depend on this L, but it's also, well, you will see in a minute why 2D is the most interesting, at least from that perspective that we have. So the last thing about this correction. What does it tell us about the beta function? Remember, we have a beta function d log g by d log L. And in 2 dimensions, in d equals 2, it is just 0 in a metal. Yeah? D minus 2 is 0. Sorry? Yeah, but now we add this quantum correction. G and sigma are the other thing. G and sigma in 2 dimensions is the same, because conductance of a square equals to the conductivity per unit square. Only in 2 dimensions. That's one reason why we like studying 2 dimensions. So if we put this delta sigma here, this will be 1 over g dg by d log L, right? The derivative of the logarithm is just dg by g. And this delta sigma is what we have here in the numerator, and log L is what we have in the denominator. So this derivative is just this prefactor here. So we get minus e squared over 2 pi squared h g. And as you can see for yourself, the right-hand side is explicitly a function of g and of nothing else. Yes?
Since the classical limit corresponds to h bar going to 0, how does this work?
H bar, you mean H bar, yeah? Good question. I don't know. Well, actually, let me think for a moment. This is a correction to the conductivity, which should be absent in the classical limit. I'm sorry, I don't know, really.
But if
Yes. No, if you send h bar to 0, it doesn't mean you send e squared to 0.
Isn't it correct that this is actually a quantum of conductance?
Yes, this is correct. This is correct.
So it normalizes over e squared divided by h bar.
And for
Yes. Yeah, this is a quantum of conductance here. Yeah, that's true. No, of course. The question was what happens if we take the limit h to 0? How will this correction disappear? It looks like it will grow if you take h to 0 and not disappear. And I don't know the answer to that one. But yeah, quantum of conductance, of course, it's like, I forgot, 13 kilo or something like this, yeah. So what I'm trying to say, once again, we did the calculation. We had many interesting numbers here, like electron charge, density of states, diffusion constant, mean free time. There are many parameters. Everything cancelled out. Everything cancelled out. Only electron charge and h remained, and g itself. This means universality. So we somehow proved in this particular limit, in this particular case, we have proved that, no, I will not go back, I will draw it once again here. What we have just shown is that in this two-dimensional plot with beta function, let me now, actually it's, wait, yeah, with a beta function, d log g by d log L is a function of g only in two dimensions. If we are in a good metal, we are somewhere far here on the right, we have beta function equal to 0 with a small quantum correction which is negative and which behaves as 1 over g. So we approach 0 from below. And this thing is exactly this. Of course, this is not a proof of the scaling hypothesis. It just tells us that previously we knew from the Ohm's law from classical physics that it should be 0 in this limit, and now we've found a quantum correction, which means deviation from 0, but a negative deviation. And we can more or less still connect it to the insulating part like this.
You mean that the x-axis is logarithm g, right?
Sorry?
You mean that?
No, now it's just g itself. I mean, it doesn't matter, you can
Okay, but in the limit of insulator, it will be.
Oh, sorry, right. In the limit of insulator, it will be some different curve then. Yeah, you're right. I will remove it. Yeah. If you put g equal to 0, it means that you are in the perfect insulator already.
You draw this line, so if we go further on this line, we will go to minus spin, so we can go to the linear.
This plot does not exist on negative values. Sorry, it's not log g, it's just g itself. It will go like this. Oh, sorry. It goes like this. And this is called insulator. Okay, if you give me 5 more minutes, I will do another. So you will not give me 5 minutes, okay?
I have a quick question that it's a good result, but the first thing I think about this result is there experimental information that says that exactly yes, this is the correction?
Yes, this correction is very well measured experimentally in many different materials, and it's indeed exactly like this. You can search by the keyword negative magnetoresistance. This is what is usually called weak. This is called weak localization correction. Weak localization. Localization because it's negative, so it somehow tries to localize electrons. And this is called weak localization correction. It also depends on the external magnetic field, which I did not discuss, but this is the easiest way to measure it. To measure its magnetic field dependence, and it's very, very, very well established. So, what I also wanted to say is there will be no more integrals in this lecture, only some algebra. Let's now recall that true electrons have spin. Electrons have spin, and we have two possible projections of the spin, like up and down. So the real conductivity sigma, which is E squared times nu times d, yeah, actually should also include 2 due to spin. Don't take it literally, usually it's included inside nu. I mean, you have twice more states, so you can double the density of states, and then your Einstein relation remains intact. But I can say this is nu, this is density of states without spin. That's why I add spin explicitly here. I ran out of my notes. How did it happen? Sorry. they're here. Yeah, so with spin, sigma is 2. Delta sigma, correction to the conductivity, I will restore this thing with, with the logarithm. Minus e squared 2 pi squared h logarithm. Minus 2, minus e squared over 2 pi squared h log L over L. I will also multiply it by 2 due to spin. Just if you have spin, but it is decoupled, it's not coupled to anything, you have like 2 copies of your system for spin up and spin down. Each copy has this conductivity, and in each copy you have this correction, so you just add them up. But now if you ask what happens in terms of the diagrams, we have a Couperon ladder. Let me remind you, a Couperon ladder. Couperon is a ladder with 2 arrows in the same direction with these dashed lines. And we now have spin. So each green function depends not only on momentum and frequency, also on spin. But spin is completely decoupled from everything. Spin is conserved, which means that if we have spin up, for example, on the entrance, we will also have spin up at the other end. When electron scatters, the spin remains the same. And if we have spin up here, we will also have spin up here. And the rest will be the same. And this is called the Couperon with 2 spins up. And in a similar way, I can define a Couperon with 2 spins down, and also with 1 spin up and the other one down. So there are actually 4 different Couperons, 4. And there is a very nice basis in this double spin space, which is the following. Up, up, minus, down, down, also the square root of 2, and up, down, plus or minus, down, up, also the square root of 2. I have in total 4 different states. 1, 2, 3, 4. There are 2 here inside. This, I will never learn this. Okay, this thing is called singlet state. And these 3 states are called triplet. These are just names. So I have 4 Couperons in total, and they're all equal. This expression for them is the same irrespective of the spin. So I can take any linear combinations of these spin states and I will have the same expression. And actually these linear combinations are much better. One is singlet, it's up, up, plus down, down, which means a Couperon, like for a total density, I sum up spin up plus spin down. I compute how this Couperon propagates irrespective of spin. And this thing is spin dependent, yeah, up, minus, down, or up, down, minus, down, up. They are triplet. In other way, you can say that this singlet Couperon corresponds to 2 spin states which have a total spin 0, and these have a total spin 1 with 3 different projections. And this correction to conductivity, delta sigma, was a diagram with a loop with the Couperon. So my question is, this delta sigma, which equals, once again, minus 2 e squared, minus e squared over 2 pi squared h. There was this extra factor 2, I will put it like this, log L of L. So I'm asking, we have 4 different couplings, but our correction has only factor 2 here. How this 2 comes up from which couplings contributed? Which of these 4 couplings contributed to this correction?
Can I ask a question?
No, you cannot ask a question until the end of the lecture because we are very much behind the time. I'm sorry. I will answer. You cannot ask the question. I will answer afterwards, okay? It will happen in 5 minutes. Please let me finish. I'm sorry. The question, how these 2, which of these 4 couplings combined to make this number 2? Sorry? You mean this? Actually, no, but it's almost correct. The true answer is like this. All 4 couplings contributed, all 4, but one of them with a positive sign and 3 of them with a negative. So this negative correction with an extra factor 2, this 2 is actually 1 minus 3. And there is a very specific case. If you take all the same system and add to your Hamiltonian or to your metal or to whatever strong spin-orbit coupling, which usually happens in some materials. Spin-orbit coupling means that your spin is no longer a conserved quantity, but whenever the electron scatters, it can also flip the spin. Or your bands in the spectrum are split according to spin. Strong spin-orbit coupling actually means that triplet couplings are suppressed. Remember, I told you on the very first lecture that diffusion pole, the pole in the diffusion, the 0 in the denominator, is related to a conservation law. Now we have some extra diffusion-like poles. We have coupling, which can also become 0 at 0 momentum. I mean, the denominator becomes 0. And here we have even 4 different couplings. And this all corresponds to some new conservation laws. For example, these correspond to conservation of spin. Spin up, when you scatter, remains up, so it's conserved. The density with spin down is conserved independently. If you have strong spin-orbit coupling, only the total density is conserved. Spin density is not conserved anymore, which means that these triplets are suppressed and only the singlet, which corresponds to the total density, will remain. So in a system with a strong spin-orbit coupling, triplet couplings are suppressed. I will not do this calculation, but it also means that this minus 3 will not happen. Their contribution will not be added. So in a system with a spin-orbit coupling, strong spin-orbit coupling, delta sigma equals plus E squared over 2 pi squared h logarithm, and is actually the same as in the usual system, but with an opposite sign. This effect also has a name. It's called weak anti-localization. That one was weak localization. This one is weak anti-localization. And it also means that we have a universal beta function which at large g approaches 0 in 2 dimensions, but from above. And then it still goes to an insulator with small g. So the conclusion: there is not a single beta function. We found 2 different beta functions depending on whether we have strong spin-orbit coupling or whether we don't have strong spin-orbit coupling. This is important. Spin-orbit coupling changes the beta function. All other details do not, but this does. And actually it has a name. This case, when we don't have a spin-orbit coupling, spin conserved. If spin is conserved, this case is called, for some strange reason, orthogonal. It's just a name for now. And if spin symmetry is broken, like with the spin-orbit coupling, if the spin symmetry is broken, this situation has a different name. It's called symplectic. And in these two situations, we have different beta functions. Moreover, in the symplectic case, when the spin symmetry is broken, our beta function, we have just proven it, crosses 0, which means that the yellow statement that there are no metals in 2 dimensions is not exactly correct. There are metals in 2 dimensions if you break the spin symmetry. Then this is a metal insulator transition, and you can have materials which behave like metals with growing the size. Due to anti-localization, their conductance grows and becomes infinitely large, and there are materials that still are insulators in 2 dimensions, but only when spin symmetry is not conserved. That's the end of today's lecture, and now I'm ready to answer any number of questions you have.
I have a question about just what you said, that why single is plus and triplet is minus? You just stated
Sorry?
so 1 minus 3.
Because I know that the result should be -2, and it should be composed of 4 components. Yeah, of course it's a guess.
There is some derivation.
Yes, there is a microscopic derivation starting from a Hamiltonian with spin-orbit coupling that leads to this result. I wanted to show you, to convince you that this result is correct without doing actual calculation. That's why I chose this way. If you're interested, it's not actually hard. You can do this calculation. Yeah, please.
I have 2 questions. First of all, usually the basis of two electron system is chosen in such way that you have 2 vectors, one in singlet and one in triplet, which consist of 2 basis vectors, and 2 others consist of just 1. But
Sorry, I didn't get you.
okay, usually we have basis up down minus down up for singlet, and up down plus down up for triplet with the 0 spin projection, and 2 other triplet components with first one which is up up, and the second is down down.
Very good. This is the same basis,
Better.
but up to a time reversal operation applied to the second spin. Because usually singlet and triplet are defined for diffusons, not for couperons. And for diffusons, they look exactly like you wanted. But then when you flip the arrow to make a couperon, you transpose the green function, which also acts in the spin, and it changes spin up to spin down to spin up, changes spin up to spin down, and spin down to minus spin up. And then you get these states, and they look exactly like you want, because this is total density.
Okay, but in this case, the basis vector of up will go to up down.
Up is changing to down, down is changing to minus up.
Okay, so anyway, you will not have such 2 triplets.
Please come here and do a simple thing. Up changes to down, down changes to minus up.
I suppose
No, for this state. For this state,
Just a second, I'm interested about...
wait, no, I'm here, I'm the boss here. You take this state and you apply a time reversal operation to the second of these two spins. So what you get?
That's okay. And that's completely okay.
So singlet is correct.
Yes, of course.
Great.
But I have a question about this one.
What's wrong with this one?
So it will become
Up, plus or minus, down, down. Yes.
yes.
What's wrong with this?
But usually it is just up or down, down.
Let me tell you something. There is a science which is called physics. And in physics, we usually classify states with a total momentum 1 by their projection on the axis z, which is plus 1, 0, minus 1. And yes, this is projection 0, and these two, the way you want them, would be projection 1 and projection minus 1. But actually, there is an alternative basis, which is usually used in the science which is called chemistry. For states with momentum 1, which are p states in the atom, they have basis x, y, z. P orbital in x, y, z, and these are they. This is the zero projection on z-axis, zero projection on x-axis, zero projection on y-axis.
Okay.
And it's much, actually, for this particular case, for L equals 1, it's more convenient this way.
And my second question was that to calculate conductivity, we should connect this Cooperon with these corners. Yeah.
Yeah.
So, and how they interact with the spin. So are they?
It's like this. One of them is plus 1. So for singlet, when singlet spin state goes, it is plus 1. When triplet goes, it is minus 1.
Okay, so we can explain the sign by just
Yes.
description of this.
Yes, but you have to add spin indices to every green function, and you should look carefully all traces, how they are connected. That's what I wanted to avoid. Please.
For this calculation, especially when you call that Cooperon is the same as diffusion, works only because of we work with quadratic spectrum.
No. We don't work with the quadratic spectrum.
Okay, in this case, why Cooperon is the same as diffusion? Because if you go,
This is a very good question. I unfortunately didn't have time to discuss it. Cooperon is the same. Cooperon is the same as the diffusion, provided your system has time reversal symmetry. So what you say, when I say p to minus p, it's kind of reversing time. Actually, you can have time reversal in a system with more complicated spectrum than parabolic. So actually, you're right. Time reversal symmetry is required in order to get this type of correction.
Okay, in this case, for each system, I can use this result.
Which one? Which of these two?
All this.
This you can use for a system with time reversal symmetry and with spin symmetry, which is called orthogonal. And that one for a system with time reversal symmetry, but with broken spin symmetry, which is called symplectic. That's it.
Okay, if I ask you about what if my system don't have time reversal symmetry?
This
how-
will be a third case, which we did not discuss yet.
Okay.
Yeah, actually, I can answer. It's very simple. Yeah, there is a third case. Sorry. It will be just 10 seconds. Which is called unitary. When time reversal symmetry is broken, delta sigma is 0. I mean, all Cooperons are suppressed, not only triplet, but also singlet. So this thing becomes 0, and then there is a third curve here, which goes like this. Time reversal is broken if time reversal... Yeah, I will repeat this whole thing next time,
Okay, but
because not everybody... Yet it's called unitary, and it has a third type of beta function, which is in between these two.
if we take a look at diffusion and Cooperon, and if I want to compare them in this case when I don't have time reversal symmetry, how is it?
Diffusion is the same, it didn't change. And the couperon will have dq squared minus I omega in the denominator plus some constant,
Okay.
which is called mass. People say couperon acquires a mass. Due to breaking of the symmetry, it acquires a mass, it decays in space, and the integral is no longer logarithmically divergent, or this logarithm is cut not at the system size, but at some finite scale, and that's why we don't include it. I'm sorry for the delayed lecture.
Yes.